This is another question on finding eigenvalues and eigenvectors. So let me write the question. We saw a similar question in the previous video on finding eigenvalues and eigenvectors. So the question is, find the eigenvalues and the eigenvectors of the matrix A, where A is given as follows. So we saw how to find eigenvalues and eigenvectors in the previous video. Let us recap it just quickly. So we saw the eigenvalue problem. It is given as follows: Ax equal to lambda x, where A is a square matrix. X is the column vector, which is the eigenvector of the matrix A, corresponding to the scalar lambda, which is eigenvalue of the matrix A. So how do we find the eigenvalues? Well, we consider the following characteristic equation. This characteristic equation, that is determinant A minus lambda I equal to 0. So we will solve this characteristic equation, and the solutions or the roots of this characteristic equation are the eigenvalues lambda I of the square matrix A. Now how do we find the eigenvector? Well, each eigenvalue will have an eigenvector associated with it, and then we will use this eigenvalue problem definition. Ax equal to lambda x, we'll use precisely this equation, this same thing we have written over here. So we will solve this system of equation to give us the eigenvector, the components of the eigenvector for the eigenvalue. So that we will be able to find out the eigenvector xi corresponding to the eigenvalue lambda I. So it is a simple procedure to find out eigenvalues and eigenvectors. So let us come to our question. We are given this matrix and we need to find out the eigenvalues and eigenvector. So let us write down the characteristic equation. The characteristic equation is given as follows. So this would be like so. So this gives us the solutions as follows: lambda 1 equal to 1, lambda 2 equal to again 1 from this term, and then lambda 3 equal to negative 1. So we have a repeated eigenvalue over here. This repeated eigenvalue, these eigenvalues are not distinct. So this is something known as degenerate eigenvalues. So this is degenerate, and since two eigenvalues are the same numerical value, so it is known as doubly degenerate eigenvalue, and lambda 3 is a distinct eigenvalue. So let us now find the eigenvalues. For the eigenvalue of 1, note that this is doubly degenerate, so we will get two eigenvectors corresponding to this lambda equal to 1. So we have the equation. Let us write it down. So the augmented matrix form of this system of equations would be as follows. Now we will use row operations and do row reduction to get the reduced row echelon form. So the first operation would be as follows. So this is the reduced row echelon form. Now this corresponds to the following system of equations. And x can take any value. So for the first eigenvector, let's take x equal to 0 and y equal to z equal to 1. So this gives the eigenvector. Let us take it 1 over square root 2 for normalization. So this is one combination, and another combination we can get is by swapping the 1 and 0. So x equal to now 1 and y equal to z equal to 0. So this gives another distinct eigenvector. So notice that these eigenvectors are normalized as well as they are orthogonal to each other. So typically we would want normalized and orthogonal eigenvectors, and the eigenvectors should be distinct. They should not be scalar multiples of each other. For example, if I would have taken, let us say, x equal to 2 and y equal to z equal to 0, this would give us this, but this is just a scalar multiple of x2. So this is not a distinct eigenvector. We want distinct, normalized, orthogonal eigenvectors. So this is not a good eigenvector in the sense that this is same as this, essentially same as this, just a scalar multiple. And or else, for example, we could have taken x equal to 1, y equal to z also equal to 1, and for normalization, let us say we'll take 1 over square root 3. So this gives the eigenvector like so. So this is a valid eigenvector. This is not a scalar multiple of existing eigenvector, but this is not orthogonal. This eigenvector, let us say if this would have been our x1 prime, then x1 prime and x2 are not orthogonal. And similarly, x1 prime and x1 are also not orthogonal. So we could use Gram-Schmidt orthogonalization to make these orthogonal, but it is always a good practice to start off with normalized orthogonal eigenvectors. So scalar multiples are definitely not allowed, and this is allowed, but this is not really a very good way. Having orthogonal eigenvectors is always nice and helpful. So this should be kept in mind when working with degenerate eigenvalues, because in the degenerate case, just a single value, just a single eigenvalue of lambda equal to 1 will give rise to two eigenvectors if it is doubly degenerate. If it is triply degenerate, then we will have three eigenvectors corresponding to an eigenvalue, and so on and so forth. So we should make sure that our eigenvectors are normalized and they are orthogonal, and they should definitely not be scalar multiples of existing eigenvectors. So let us now look at the next eigenvalue. It's -1. So again, let us write the augmented matrix form. And let us now apply row operations. So this is the reduced row echelon form. And this corresponds to the following set of equations. And let us set this equal to 1 over square root 2 for normalization. So this gives us the eigenvector as follows. So we have now solved the question. We have 3 eigenvalues and 3 eigenvectors. 2 of the eigenvalues have numerically the same value and they are doubly degenerate. So let us write down the final results. So for lambda 1 equal to 1, we get 2 eigenvalues let me just check what x2 was. It's 100. So these are the 3 eigenvectors that we have corresponding to the eigenvalues, out of which lambda 1 is doubly degenerate. As a result, it has x1 and x2, two eigenvectors. Notice that all of these eigenvectors that we have are normalized and they are orthogonal to each other. So that means they are orthonormal. So normalization and orthogonality makes it orthonormal. So x1 is orthogonal to x2, x1 is orthogonal to x3, and x2 is also orthogonal to x3, and each of them are normalized. So this solves the question in which we had to find eigenvalues and eigenvectors for a given matrix. And the takeaway from this video is that we can have degeneracy in the eigenvalues. Degeneracy is possible. That means the eigenvalues will have numerically the same value. So repeated eigenvalues we can have, and that would mean that for just one numerical value of the eigenvalue, we might get multiple distinct eigenvectors. By distinct, I mean they should not be scalar multiples of each other. So this concludes the question.